All right, so I'm going to make a quick video here just to do a few more of these questions algebraically. We encountered one of these complex fraction questions earlier. I'm going to go ahead and do number 9. A couple ways we could do it, and I would definitely say the most efficient way is to look at all of the little fractions. So x over 4, 4 over x, 1 over 1, and 4 over x, and say, all right, what's the least common denominator of all these little fractions? And looking at it, I'm going to say the least common denominator is going to be 4x. So if I go ahead and I distribute a 4x into the top of the big fraction and a 4x into the top and bottom of the big fraction, I'm multiplying by 1. So I'm not changing the fraction itself. I'm just changing the way it looks. So I'm going to get a new limit expression here. I'm going to get limit as x goes to 4. All right, so if I go ahead and I multiply 4x into x over 4, well, the 4 cancels with this 4, and the x doesn't, so I get x squared. And if I multiply the 4x into this fraction, the x cancels, but not the 4. So I get 4 times 4 is 16. In the denominator, when I distribute the 4x times 1, nothing cancels, so I just get 4x. And when I do 4x times 4 over x, the x cancels, but not the 4. So again, I get minus 16. So again, if I try to plug in 4, I get 16 minus 16, which is 0, and 16 minus 16, which is 0 in the bottom. So still a determinant form, but I can go ahead and I can factor. I can factor the top. The top is a difference of perfect squares, factors into x plus 4x minus 4. And the bottom, if I pull out a GCF, I get 4 times x minus 4. And there's kind of our key here, right? If I plugged in 4 and I got 0 over 0, probably means that x minus 4 is going to be that common factor. That cancels. So one of the things that I might have neglected to mention is that when that happens, when we can cancel out those factors, that results in the possibility of a removable discontinuity, or what we talked about as a hole in the graph. So what doesn't cancel is this x plus 4 and this 4. So I get x plus 4 over 4. So if I graph these functions, it's a linear function, and it's going to be identical to this ration, or to this original mess of a complex fraction. So you can see it here. Taking advantage of Desmos, I typed in the original limit expression that we were evaluating, and it looks so messy, but when I graph it, I get a linear function. Interestingly enough, a linear function with a y-intercept of 1 and a slope of a fourth if I go up 1 over 4. And the tricky part about this is it looks like your standard linear function, but there it is, right at 4, it says it's undefined. In fact, you could even see that it shows it as a hole here as when I capture that point. Now, if I'm not clicking on it, it just looks like your standard graph. And if I zoom in on that point, and no matter how close I get to x equals 4, the pixels across the screen are going to fill in that gap, because I can get infinitely close to 4, and it's still going to look as though it exists at x equals 4. But in reality, it doesn't. And so we need to kind of comprehend that as something that we're focusing on, that when we look at this, it's hard to see that it's actually a removable discontinuity. So there again is our equation. You would see if I distributed with division of 4, slope of a fourth, y-intercept of 1. And essentially any of these questions that originally, if I start with plugging in 1, right, on number 11 here perhaps, I'd get the square root of 4 minus 2, which is 0 over 0. And if I can simplify it and actually come up with a limit at that point, that means that I'm going to have a removable discontinuity at x equals 1. And for this one, I'm probably going to have a removable discontinuity at -3. And for this one, there's a chance of a removable discontinuity at maybe -1, and so on and so forth. Now, actually taking a closer look at this, already looking at 13, it's asking me for the limit as x goes to 1. Well, if I plug in 1, I get 3 minus radical 2 over 2. Now, that wasn't 0 over 0, so that means that that's not a removable discontinuity. So this one, just by direct substitution, I get 3 minus radical 2 over 2. And that's just what it is. So a limit exists pretty much anywhere, unless there's non-removable discontinuity, like a jump that can happen in a piecewise function or a vertical asymptote. But let's take a look at maybe example 11. Again, if I plug in 1, we already got 0 over 0, so let's talk about how we simplify that. If I multiply the top and bottom by the conjugate, we did this example or a similar example to this before. When I multiply out up top, the radicals cancel and I'm left with the radicand that's underneath. So x plus 3. And then the outers and the inners would be 2 radical stuff and -2 radical stuff, which would cancel. So then I'm really focusing on this, which would be -4. So when I combine that, the top really is just x minus 1, and the bottom is x minus 1 times the conjugate. So again, I'm not going to distribute that together based off the fact that that kind of told me probably going to have an x minus 1 that cancels. So now this is the same as the limit as x goes to 1 of 1 over radical x plus 3 plus 2. And if I plug in 1 into that, I get 1 over radical 4 plus 2, so I get a fourth. So now that I'm realizing this, I'm going to actually go in and take advantage of Desmos again. In fact, actually, when I look back, I'm going to go back to example 9 for a second because I never actually answered the question, did I? It was asking me for the limit as x goes to 4, and that's for this one is 2. When I plug in 4, right? And so if I go back to Desmos, we can see that here, the limit as x goes to 4, the y value appears to be approaching 2. So if I go back to that other one with the radical, and I graph that on here, I should expect it to be approaching a quarter. So here I've plugged it in, and you can see that at x equals 1, it almost looks like, again, pay attention to the scale here, halfway between 0 and 0.5. It is 0.25. So if I click on it and it says that it's undefined, you can see that the hole is visually represented. As soon as I go slightly to the right, 0.248, 0.249, and if I get close enough, it might even tell me, yeah, 0.25. It's not actually 0.25, but pretty close. All right, so that covers, I'd say, the rest of algebraic limits. The next, we'll be talking about infinite limits.